new physical constant without any reason.
He wrote, a theoretical interpretation had to be found at any cost, no matter how high. So from that moment on, he dedicated himself to finding one. He later reflected that after some weeks of the most strenuous work of my life, light came into the darkness, and a new, undreamed-of perspective opened up before me.
He introduces what we now call Planck's constant, and it has the units of action. Planck's constant h is a quantum of action.
Planck later proposed that anytime any change happened in nature, it would be some whole multiple of this quantum of action.
So it's kind of spooky. This breakthrough that starts the ball rolling toward quantum theory brings action in, not energy and not force, action. Gives you a hint.
At first, the quantum of action got little attention. That is, until a 26-year-old patent clerk came on the scene. In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. It was telling us that light actually comes in discrete packets, or photons, each with an energy hf. Einstein used this insight to explain the photoelectric effect, how light can eject electrons from metal, but only when the frequency is high enough. If the frequency is too low, no electrons will be emitted, regardless of the intensity. The idea of quantization spread. 8 years later, Niels Bohr was trying to understand how an atom is stable if it has a positive charge in the center and negative electrons whizzing around it. Why don't they just spiral into the nucleus, radiating their energy as they go?
And what he wants to do is, he says there's something fishy about something being discrete. That seems to be the new, ambiguous, weirdo lesson of the new quantum of action.
Bohr realizes that as the electron goes around the nucleus, it has an angular momentum. Mass times velocity times radius. So angular momentum has the same units as action.
And so what he decides to do is discretize the orbital angular momentum for no good reason. He says, let me slap that on and say angular momentum of the electron can only be in 1 unit, 2 units, 3 units of the same quantity h. And because it's talking about motion in a circle, the factors 2 pi come in, so it's really nh over 2 pi, what we now call nh bar.
This comes out of nowhere. There seems like absolutely no good reason why angular momentum should be quantized. But by doing it, Bohr finds the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one, the energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum.
And that was a pretty startling thing to have fall out. I think that really was compelling. It takes some quantity with units of action and apply some, again, kind of ad hoc discretization or quantization to it.
Now, although it worked spectacularly well, no one could make sense of it. That is, until 11 years later. For his PhD, Louis de Broglie was contemplating the recent discoveries in physics, and his big insight was that if light could be both a wave and a particle, then maybe matter particles could also be waves. He proposed that everything, electrons, basketballs, people, absolutely everything has a wavelength. And he defined this wavelength analogously to light, as Planck's constant divided by the particle's momentum, or mass times velocity. Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom is if it exists as a standing wave. That requires that a whole number of wavelengths fit around the circumference of the orbit. You could have 1 wavelength, or 2 wavelengths, or 3, and so on. So the circumference 2 pi r must be equal to some multiple n times the wavelength. We can sub in de Broglie's expression for the wavelength to get that 2 pi r equals nh over mv. But we can rearrange this to get that mvr, the angular momentum, is equal to nh over 2 pi. That is precisely Bohr's quantized angular momentum condition. But now we have a good physical reason why it's quantized, because electrons are waves, and they must exist as standing waves to be bound in atoms.